Rates of reactions. Rates of reactions. Right. In rates, right, the word rate, it means, it's talking about the speed, right? It's talking about the speed at which something occurs, right? You can think of driving a car. A car can be moving at a very high speed or at a low speed, you see. So it's very nice. It's very nice that we can experience that in a car. So in terms of rates, it is the same thing, né? When you talk about reaction rates, we are also talking about how fast a reaction takes place. How fast is the reaction taking place, or how slow is the reaction taking place? But actually it's how fast, yeah, because a reaction can be taking place very fast, or a reaction can be taking place very slow. Right. To give you an example, good people, of that, before I even say to give you an example, good people, when I'm saying to you we're discussing how fast a reaction takes place. When I'm saying how fast a reaction takes place, what is very key there is that the fastness or the slowness of a reaction is determined by how fast the reactants are being used up. Okay, how fast the reactants are being used up, or how fast the products are being produced. Okay, the fastness of a reaction depends on where are you looking at it from. Are you looking at it from the perspective of the reactants, or are you looking at it from the perspective of the products? That is why the formal definition for rate is the change in concentration of the product or reactants per unit time. This is the formal definition, and please know it because it's always gonna be there. This is your 2 marks that I'm giving you for your paper 2. I'm giving you right now. Okay, take your 2 marks. The change in concentration of the products or reactants per unit time. Now, what this means in isiZulu, it means how fast the reactants are being used up, or how fast the products are being produced. That's what it means. So, how can I actually, relate this to real life? Ne? Now, it's very simple. Let's say you decide to cook magwenya, right? We call these things, guys, magwenya is a Sesotho word for fat cook, right? Of which fat cook is an Afrikaans word for fat cakes, right? So I'm gonna give it to you in all languages. Amagwinya is, fat cook of fat cakes. Now, if you are making 60 magwinyas in 1 hour compared to someone who's making 100 magwinyas in 1 hour, that means the one who's making 100 magwinyas per 1 hour, it means that person is very fast in making magwinya and you are slow, right? If it takes you 2 hours to go to school and to cover a distance of maybe 5 meters, and someone, it takes them 1 hour to cover the same distance, it means the one who took less time is fast. But you have to understand that some factors have to be kept constant there. Okay, so that's why we are saying same distance, and then same type of magwinya, you should be cooking, right, and the likes. So since we are saying that the rate of a reaction is the change in concentration of the products or reactants per unit time, that means how fast the products are being produced, how fast the reactants are being used up. Because essentially a reaction is A plus D producing C plus D, right? So this part, that would be your what? Your reactants. And then this part, that will be your what? That will be your products. So how fast are we having C and D, or how fast is A and B being used up? We have to understand that the reactants get used up. We have to understand that products are produced. We have to understand that the concentration of reactants, decreases as a reaction is occurring. The concentration of the reactants decreases, meaning it goes down. But the concentration of products, what does it do? It increases. It increases because they are products, guys. Okay? The concentration of reactants decreases, meaning A and B over time. Over time, A and B are decreasing. If you had 5 grams of A, after some time you might have 4 grams. After some times you might have 3 grams, 2 grams, 5. You understand me? So we can actually describe that graphically to say, if I were to have the graph, my team, I was talking a lot of English today. I can hear that the bundles, they are depleting. Okay, so for A, if I can have the graph of A, I can either talk about the volume of A, or I can talk about the mass of A, or I can talk about the concentration of A. The fact is that the graph is going to be like this when I look at it over time. So A is being used up. If I look at the graph for B, how will the graph for B look like? Whether I'm looking at the volume of B, whether I'm looking at the mass of B, whether I'm looking at the concentration of B, the fact is that the graph is going to be like that with time, because B is being used up over time. But what about the graphs of C and D? Well, for the graphs of C and D, it will be quite the opposite. For the graphs of C and D, what we're going to observe is that if I were to look at the graph of C, whether I'm looking at its volume, or I'm looking at its concentration, or I'm looking at its mass, the fact is that the graph is going to be like this with time. What does this mean? This means that it starts being produced, and then it becomes constant. Here, whereby it is constant, whereby the graph is constant, it means the reaction is complete. Reaction is complete, meaning it's done, it has ended. There is no more C that is being produced. That is why you no more see you no more see the graph going up. It just becomes constant because no more of C is being produced. Right? If you are cooking magwenya, if you are cooking pap, if the maize meal, which is the reactant, if it gets used up, then you no more have pulp that is being produced. That's why the graph is going to be constant. Right. Same thing with the graph of D. So this can be the graph of C, or it can also be the graph of D. Same thing. As long as they are products, the graph will look like that. And then as long as they are reactants, the graph will look like that with time. Right? I hope that is clear. So I hope we understand the clear difference between reactants and your products. What should we also then know about these two things? If I want to then measure the reaction rate, right? If I want to measure the reaction rate, measuring the reaction rate, there are different ways in which I can use to measure the reaction rate. Now, what is the first method? The first method is that I can take what you call I can say maybe if the reaction is happening in this container, right? If the reaction is happening in there, I can take a tube, right? I can take a tube, connect it to the container, connect the tube into the container, and then connect that tube into a syringe outside. Connect it to a syringe that is outside like this. In that syringe, I'll be able to what? I'll be able to collect maybe the gas that is being produced. So you can measure the reaction rate by measuring the gas, by collecting the gas that was produced. If I can collect the gas that has been produced over time, right, that will mean that I'll be able to tell how fast the reaction was going, whether the reaction was moving slow or whether the reaction was moving was very fast. But the graph that I'm going to have is going to look like this. This graph here is going to be the graph of the volume of the gas. I could be collecting hydrogen, I could be collecting carbon dioxide, right? Those are the most common gases that we collect. Once I collect those gas volumes within a specific period of time, because those gases or volumes are products, right? This is why the graph is going to look like that, because I'm collecting the product. So here it's very important to understand that we are collecting a product. Why are we saying we are collecting a product? Because we are talking about a gas that has been produced, which is a product. And that's why the graph is going to have this general shape for the products. The graph for reactants is like this, okay? So that is one way of measuring the rate of a reaction. What is another way? Another way, which is number 2, I can measure the color change, right? So I can have my reaction happening here, and then as my reaction is happening there, I will take a paper, right? I'll take a paper, and then on that paper, I'm going to draw an X, okay? Oh, no, sorry. This one is not measuring the color change, but we are measuring the amount of precipitate produced. Amount of precipitate produced. So what do we mean by precipitate? Some reactions, when they occur, they produce a precipitate. And the one reaction that always produces a precipitate that you're going to be asked about is the one for sodium thiosulfate, okay? It's the one for sodium thiosulfate. This reaction is the only one whereby, or is the most common one whereby you're producing a precipitate. What is a precipitate? A precipitate is simply a solid. So what happens is that if you take your eyes, right, if your eyes are here and then you are looking at this thing that is being produced, right, if you check inside here, my drawing is very bad, right? But essentially what is happening is that as you are producing the precipitate inside, it's going to be blocking the view of this X. So because it blocks the view of the X, that tells us that the reaction is going on. So we can measure the amount of time it took for the X to be, blocked from our view. That time is going to give us the reaction rate. So that is one way of measuring the reaction rate. Okay. And I do have this. I don't know why I'm not finding my presentation, guys. I have this nice presentation on rates of reactions, and trust me, I will find it now, and then yeah, and then we're gonna yeah, I will find it now. Don't worry. Okay, so that is what we have. We can either be measuring the precipitate that has been produced, which is the solid, or we can collect the gas. Number three, what can we also do? Another thing that we can do is that we can measure the amount, the mass loss. We can measure the mass loss of reactants. We can measure the mass loss of reactants. Now, how does this one work? So how it works is that here's your container there, right? In your container, you know that there are reactions going on there, right? Between the reactants, and now products are being produced. So what you can do is that you can take some cotton wool, right? You can take some cotton wool, and then you put it there, right? Now, as you put it there, what is it going to do? It's going to allow, they're going to ask you what is the importance of the cotton wool. The cotton wool is going to allow gas only to escape. So it only allows gas to escape. Allows only gas to escape. By the way, the reactions in which you are collecting gas, guys, those type of reactions, right, they are called gas forming reactions. Gas forming reactions. Whenever you are dealing with gas forming reactions, the gas that is formed, you can measure, you can collect it, and thus measure the reaction rate, right? So gas forming reactions, the most common ones that you are dealing with in grade 12, there are only two. No, there are a lot, but the most common ones is when you have a metal plus an acid. A metal plus an acid will always produce metal plus an acid. Do you remember from grade 10 what we said? Metal plus acid always produce a salt plus hydrogen gas. Okay, salt plus hydrogen gas. Or you can have a metal carbonate, right? You can have a metal carbonate reacting with a what? Reacting with an acid. What are you going to produce? Here you're going to produce salt plus water plus carbon dioxide gas. Plus carbon dioxide gas. Right, which is CO2 gas. Okay, so those are the most common gas forming reactions that we have. Gas forming reactions. So if ever you have a metal, that metal could be aluminium, that metal could be sodium, that metal could be copper, that metal could be magnesium, right? I'm talking about the most common that they like to use. Aluminium, copper, magnesium, and so many more. As long as it's a metal and you put it inside of an acid, the acids that they like is that they like nitric acid, they like hydrochloric acid, right? So the acids they like hydrochloric acid, they like HNO3, which is nitric acid. They also like what else? Hydrochloric acid, nitric acid, sulfuric acid, okay, and then more, etc. Right? As long as I have that acid reacting with the metal, the metals that they like using aluminium, they like aluminium, they like magnesium, okay, they like calcium, they like what else? Which other metal is very common? Abo copper, so they like abo copper. Okay, so and more. Okay, so as long as I react those two things, I'm going to form a salt, and then a hydrogen gas. Then if I have a metal carbonate, what do we mean by metal carbonates, right? Metal carbonates that we have things such as sodium hydroxide, we have calcium hydroxide, calcium hydroxide, and then we have magnesium hydroxide, yeah, we have magnesium hydroxide, etc. So if I have a metal carbonate and then I react it with an acid, what am I going to form? I'm going to form salt, water, and carbon dioxide. So these gases that are produced, good people, those are the gases that we collect. Ne? Those are the gases that we collect in this syringe. After collecting the gases, we can have a graph like this, which will tell us the amount of gas that was produced within different time intervals. You see, because you're gonna say here, after maybe 5 seconds, you measure how much gas has been produced. After 10 seconds, you measure how much gas was produced. Then you plot the points. After 15 seconds, how much gas was produced. After 16 and the likes. Then it's gonna tell you there. And then where the graph becomes flat, means that the reaction is complete. Means the reaction is complete, or you can say the reactants have been used up. Usually the limiting reactant. Okay, so that is what is happening there. You have a gas forming reaction, right? So that reaction, you allow it to happen in a container, you collect the gas that is produced, you form a graph like this. In the exams, you're gonna be getting those graphs, but you must understand that you are dealing with a gas forming reaction. Okay, so what about this one? This one for sodium thiosulfate, it's just like it doesn't change. It's always the sodium thiosulfate reacting with something and then it forms a precipitate there. I will show you the full reaction there. And then number 3, what is happening here whereby we're measuring the mass loss of reactants? What is happening? It's quite simple, guys. Remember here we used to collect the gas that was produced. If you don't want to collect the gas that was produced, what you can do is to measure the mass loss of the reactants. What we mean is that, how can you measure the mass loss? What we mean is that you take this whole thing, let me copy it, and then I want to take it down here so that you understand what is going on. So I'm going to come with it this side, just down here. Give me a second. So you take this whole thing, okay? Then what do? You remove the gas syringe. You remove this syringe here. You also remove here, okay? You also remove there. Then what do? You take a cotton wool. You put a cotton wool. What will the cotton wool do? This cotton wool is going to allow gas to escape. Gas only to escape. Which gas is escaping now? The same gas that you were collecting before, that is the one that you are allowing to escape through the cotton wool. But then the reactants, they remain inside. Okay? The reactants, they remain inside. So how will you know that? How will you measure the mass loss? What do? You take a mass balance. You put this on what we call a mass balance. You put it on a mass balance. Then on the mass balance, it's going to read the mass there. Okay, it's going to read the mass in grams. So when the reaction starts, you might find that the mass is around 5 grams. As the reaction is proceeding and the gas is escaping, what happens to this mass? Does it increase or decrease? Can I hear in the comments there, guys? Does it increase or decrease as the reaction proceeds? Does it increase or decrease? Right. I see you're saying that it decreased there. Yeah, that is true. Yes, exactly. So the mass is going to decrease there. So the mass of this thing is going to decrease. Now, because it's going to decrease, what are you going to have? You're going to have you're gonna have, maybe now it's 4 grams, now it's 3 grams, after maybe after 5 minutes it's 4 grams, after 5 minutes again it's 3 grams. It's decreasing. So what type of graph are you going to come up with there? The graph you come up with will look like this. This will be the mass of reactants. This will be the mass of the reactants with time. So the mass is decreasing over time. This is the graph you come up with. Okay, so this is what we call measuring the mass loss of reactants. Right, so those are the graphs that you can have, guys. The two major graphs that you have is the one for reactants and the one for products. So now you must understand, why are the graphs different? The graphs are different because here you are forming, while here you are using up the reactants. Okay, so in both of those graphs, guys, how you calculate the rate of the reaction is common, or it is the same. So how you calculate the rate of the reaction is that you're gonna say the rate. So here, when you calculate the rate, you will say the rate is equals to, now the thing is, the y-axis here, on the y-axis you can either have volume, or you can either have mass, or you can have number of moles, or you can have concentration. Okay, so the rate is going to depend on what is the y-axis there. But whatever is the y-axis, you're going to divide it by time. But if it's reactants, you're going to say, let's say you are dealing with concentration. So here I'm going to write that it's for reactants. You're going to say negative the change in concentration over change in time. You put a negative to show that you are dealing with a reactant. Okay, if you are not dealing with concentration, maybe you are dealing with volume, you're going to say negative change in volume over change in time. Okay, because the rate, the speed of something is always positive. You can't have a negative speed. So negative speed, you only have it if you are talking about velocity, but here we are talking about speed. So that's why we put the negative there, because inside here, because it's change in concentration, the answer is going to be negative. Because how do you get change in concentration? And correct, this will be concentration, this will be time. Your final concentration will be here, and then here it's going to be the initial concentration, and you read it off the y-axis there. You check it on the y-axis there. So your initial is this one, your final will be that one. Your t final will also be here, your t initial will also be there. Okay, so again, if you are dealing with mass, you're gonna say rate is equal to negative the change in mass over change in time, and then you're also gonna say the rate is equal to what you call the rate is equals to number of moles, change in number of moles over change in time. Perfect. So that's what you have. So now, what if you're talking about products? Well, if it is products like these ones there, so when you're calculating the rate, it's going to be similar. You're going to say rate is equals to change in concentration over change in time, or you're going to say rate is equals to change in number of moles over change in time, or you're going to say rate is equals to change in mass over change in time, or you're going to say rate is equals to change in volume over change in time. Okay, there you don't put negatives. Now, what will be the units? The unit here, if you are dealing with concentration, your rate is going to be mole per decimeter cubed. Here, what is going to be the unit? The unit here is going to be mole per second, or you can have mole per minute. But the standard one is per second. I'm using the standard units. And then here you're going to have grams per second. And then here the unit is going to be decimeter cubed per second. These are going to be the units for your rate there. Okay, I hope that that was clear, guys. So that is how we deal with reaction rate. You just have to understand the graph that you're working with, and then you have to understand the calculation, how to do the calculation there, and interpreting the graph itself. Okay, so another thing now about reaction rates that we have to understand, right, is that on your graph, even if I'm going to be giving you graphs like this, ne? Even if I'm going to be giving you graphs like this and the likes, when I ask you about the dependent and the independent variable, you don't look at these things and say the independent is time, the dependent is volume of gas. No, 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 no. You don't do that. Okay? Because once you start talking about dependent and independent variable, then it means you are talking about factors. You're talking about what? Factors that affect rate. Factors that affect or rate. When we say factors that affect rate, we are saying these are things, right? These are things, we don't have things in physics, but these are, we are talking in slang. These are things that either speed up the reaction, or slow down the reaction. Okay, things that speed up the reaction or slow down the reaction. That is what we must understand there. So what are those things, right? The first one could be temperature. Okay, the first one could be temperature. Now, how does temperature affect the rate of a reaction? How does temperature affect the rate of a reaction? Well, we just have to understand that a temperature is a measure. This is a measure of the average kinetic energy of particles. And then we'll discuss how it affects rate in a few seconds. So it's temperature, it's concentration of the product, of the reactant, and then it's also surface area, and then we also have state of division. But okay, surface area goes with state of division. And then lastly, it's going to be the nature of a reactant. But we're not done actually. The last one, last. Yama last. Is a catalyst, right? It's a catalyst. So a catalyst is going to affect the rate of a reaction. So these 5 factors, good people, they are the ones that, affect the rate of a reaction. Temperature, concentration, surface area, right, and catalyst, the nature of a reactant. They either speed up the reaction or they slow down. By the way, temperature can either speed up the reaction if you increase the temperature or slow down if you decrease. Same thing here, if you increase concentration of the reactants, right? So here you should understand that it's concentration of the reactants. Okay, so if you increase one of the reactants, so if you have A plus B giving us C plus D, if you increase maybe the concentration of A, then you're gonna increase the whole rate of the reaction. And then surface area, surface area, usually talking about the state of division. What we mean there is that if you have round pills, né? If you have round pills and crushed pills, which means crushed pills is powder, right? So if you have powder pills, they dissolve much faster compared to round pills. So that is why the state of division affects the rate of a reaction. Okay, so if you look at round pills and powder, powder dissolves faster than round pills. Okay, and then temperature. I think you've realized that if you put sugar in cold water and then you put sugar in hot water it's going to dissolve much faster as compared to cold water. So you have to understand that's how temperature affects the rate of a reaction. Catalyst. If you put a catalyst, right, the reaction becomes faster. An example is photosynthesis. You do know that for photosynthesis, if we didn't have things such as enzymes, right, in the leaf, then that process would take a very long time, right? So some things, they need a catalyst for them to be fast. Okay, so these are the 5 factors that affect the rate of a reaction. Now, when you're looking at any question, guys, I need you to understand that these 5 factors, these are your independent variables. Okay, these are the independent variables. Okay, so what is the dependent variable? The dependent variable, good people, is always 1, is always the rate of the reaction. Why? Because the rate of a reaction depends on these things. Okay, so they are always the independent variables, and then this is always the dependent variable in questions. Then what is a controlled variable? Then let's understand that if I want to investigate concentration, I must keep all other factors constant. So what we must understand is that you investigate one factor at a time. You investigate one factor at a time. You can't investigate 2 factors same time. So because you investigate one factor at a time, the rest become control variables. If I'm investigating a catalyst, the rest must be the same. They must be controlled. So these, all of them will become control variables. If I'm investigating concentration, temperature becomes a control variable. Surface area or state of division becomes control variable. Nature of the reactant becomes a control variable. Catalyst becomes a control variable. So you must understand that we investigate one factor at a time, and then that factor that you're investigating becomes your independent. The rest of them become the controlled variables, while the dependent is always the rate of reaction. I hope that is clear. I hope that is clear. And then since we are on that, why is it important to understand the independent variable and the dependent variable? Why is it important? Well, this is because, good people, whenever you're going to be constructing an investigative question, whenever you're going to be doing an investigative question, whenever you're going to be doing a hypothesis, whenever you're going to be discussing, so it's investigative question, hypothesis, and aim, and your aim. Ne? This is because these 3, whenever you are formulating one, ne, that is investigative question, that hypothesis, that aim must always have what? It must always have the dependent variable, it must always have the independent variable. When you are stating it, it must always have the independent variable, and then it must have also the dependent variable. Okay, that means your investigative question or hypothesis or aim is incomplete if you didn't include the word rate of reaction, because that is always the dependent variable. So how do you formulate an investigative question? You can say, what is the relationship between temperature and reaction rate? Or what is the relationship between concentration and reaction rate? Or what is the relationship between state of division and reaction rate? Or what is the relationship between the nature of a reactant and the reaction rate? Or what is the relationship between a catalyst and the reaction rate? That is how you formulate an investigative question. Or you can say, what is the effect of temperature on the reaction rate? What is the effect of concentration on the reaction rate? What is the effect of surface area on the reaction rate? What is the effect of state of division on reaction rate? I hope you get the idea of an investigative question. Then how do you formulate a hypothesis? Your hypothesis will be like, maybe the higher the temperature, the faster will be the reaction rate, or the higher will be the reaction rate, and vice versa. Or you will say the higher is the concentration, the higher will be the reaction rate, and vice versa. Or you say if it is in powder form, right, maybe the reaction rate will be faster. You are predicting. A hypothesis is a prediction, okay? And then what is aim? Aim, is what you are aiming to investigate. The aim is to investigate the concentration of reactants, the influence of the concentration of reactants on the reaction rate. The aim is to investigate the influence of the temperature on the reaction rate. You understand me, guys? Your question, your hypothesis, your aim must always have the independent variable and the dependent variable, which is what? Which is the reaction rate. Which is your reaction rate. Okay, which is your reaction rate. Okay, so that is what is happening there, guys. I hope that this is clear. I hope that all that theory there is clear. We do need to understand the theory, guys. So I'm gonna be bothering you with a lot of theory that you must understand for this topic. Now, the last thing we must understand here in terms of that, we must also understand what we call the collision theory. What is the collision theory? The collision theory is simple. It's simply telling you that for you to get I'm not advising this or anything, but for you to get a boyfriend or girlfriend, you need to go out there and meet people. You can't find a boyfriend or girlfriend while you are sitting in your room. Okay, you can do it through a phone and stuff, but we're just talking about the olden days. You needed to go out there and meet people for you to have someone. Okay, so even if it's on a phone, you are still meeting people, but now it's through your phone. You understand? What we mean here is that for a bond to be formed, collision must occur. There must have been collision between the particles, right? And you must understand that for a bond to be formed, energy must be released. Okay, so when particles collide, they release energy, and thus they form a bond. Okay, so when particles collide, what do? They release energy, which allows for a bond to be formed. Okay, so why is it important to understand the collision theory? Because since we are discussing reactions, right, since we are saying that A plus B must react to form C and D, how will they react? The reaction is by them bumping into each other. So this and that must be bumping into each other. Bumping into each other. What does bumping into each other mean in physical science or in chemistry? is to collide. So A and B, your reactants must collide for them to form a bond. How fast they are colliding or how slow they are colliding depends on which factors. Depends on the temperature, the concentration, the surface area, the nature of the reactant or the catalyst. You understand that how fast they are forming the reactions, how fast they are forming the bonds. Okay, how fast they are forming the bonds, meaning how fast they are forming those products. It depends on the collision between the two. It depends on how fast it depends on those factors that we talked about. But the collision theory is for us to understand how a bond is formed. A bond is formed through collision of particles, whereby energy is released. Okay, I hope that we are clear there. So, are we saying that as soon as A and B are going to bump into each other, they're going to form a bond? No. No. It doesn't mean that when A and B immediately bump into each other, they're going to form a bond. Let's be honest. Even if you go to the mall right now, it doesn't mean that you are going to it doesn't mean that you're going to form a relationship with every girl you meet. Or if you're a boy, if you're a lady, it doesn't mean you're going to form a relationship with every boy that you meet there in the mall. Okay, there must be that one that when you meet, you collide, you click. Once you click, that's when you can form a bond. So similarly with particles, if they bump into each other, it must be what we call an effective collision. It must be an effective collision for them to form a bond. Okay, it must be an effective collision. So how will particles collide with an effective collision? Those particles, they must have, number one, they must have the correct orientation. They must have the correct orientation, and then they must release sufficient energy. Okay, that is how they can form a bond. Okay, so it must be an effective collision. So that's what we are saying there. So guys, it's also like you, ne? If you go to the mall then you are not looking, maybe you must, have the correct orientation, meaning that you must be presentable and everything for you to be able to make that good collision, that effective collision. Okay, so that's what we're saying. So why are we talking about the collision theory? It's because when you explain these factors, how they affect the rate of a reaction, you must use the collision theory. Okay, so you're gonna have to use the collision theory for you to explain that. So that is why we must know that. So now I'm just gonna give you here how do you explain them, and then we should be okay, right? So I'm just gonna give you how you explain those factors so that you see there is just a certain trend in terms of how they are worded there. So this first one is this one. If you increase concentration, what is going to happen? Increasing concentration results in more number of particles with sufficient energy being exposed. Please put being exposed. And now, since there will be more number of particles with sufficient energy that are exposed, those number of particles are going to collide with the correct orientation, and therefore there will be more effective collisions per unit time, therefore increasing the rate of a reaction. Therefore, increasing the rate of a reaction. So please, when you are answering, you answer, it's always a formal question. So to answer those formal questions, this is how you must answer it. Increasing concentration results in more number of particles with sufficient energy being exposed, which means more number of particles collide with correct orientation, and therefore there will be more effective collisions per unit time, which increases the rate of a reaction. The decrease is the opposite. A decrease in concentration means there will be less number of particles, sufficient energy being exposed, and then therefore less number of particles with correct orientation, and therefore less effective collisions per unit time. So do not worry, I'm going to send this document into the group, so please go through it. It's going to give you how to use the collision theory. This is when they say use the collision theory. Okay, that's when they say use the collision theory to explain that. Okay, so you are gonna use it in that way. You're gonna check that temperature. You just tell them increase in temperature results in more number of particles with sufficient energy, more number of particles with correct orientation, therefore more effective collisions per unit time. Okay, so you will see that they are all similar in terms of how you explain them. Okay, so I'm going to send that document in the group, and then please go through it there, and then you'll be able to use that to explain, to use collision theory to explain why some reactions take place fast, some are taking place slow. Okay, so guys, that is 90% of reaction rates. The thing, what we are only left with right now to come, what we're only left with, number one, on our next lesson we're gonna do questions on reaction rate. Okay, we're gonna do questions, and then we're gonna talk about the endo or exothermic reactions. Then we're also gonna talk about the Maxwell-Boltzmann distribution curves, right? Maxwell-Boltzmann distribution curves. Then after we are done talking about those, we'll be done with reaction rates. So please tune into our next session there, whereby we're going to discuss that. But also expect a homework for today. The homework is exactly going to be about these reaction rates. Okay, so you just send it to me there, and then we'll check it and see if we understood that. But this is all the theory that you're most definitely going to need. So please make sure that you study this. Okay, even if you have to repeat this video some couple of times, trust me, it's gonna assist you, because I've given you everything that they're gonna want you to answer in reaction rates. Okay, so do we have any question before we divorce each other for today? Right. They usually say silence is also a very beautiful answer. Yeah, so yeah, that is it for me from me today, guys. And then watch out for the homework. We'll meet each other next time.